Hey, this is Kyle Hayden, and today I'm going to be talking about exotic ribbon disks and symplectic surfaces. So I want to start out with a bit of a plan, and we'll start by talking about some background material on exotic surfaces and the main results I want to share today. And then what I'll do is illustrate those results by focusing on construction of exotic ribbon disks in the foreball, and at the end, extending these results to give some exotic phenomena in the complex and symplectic setting. Okay, so let's begin with some background. Recall that every second homology class in a four manifold can be represented by a smoothly embedded orientable surface sigma. And now as soon as we have this statement, there's natural follow-ups, like what is sigma? For example, what's its topology, what's its genus? And now that we have this existence statement above, we have a uniqueness question. How unique is sigma? For example, is its genus determined? And it's pretty easy to see that the answer to that is no. You can always increase the genus, but let's say you fix the genus, then how unique is sigma? And then finally, how does this relate to the smooth or geometric structures that X might carry? So for example, if X supports multiple smooth structures, when I fix a homology class, does the type of surface I can use to represent it depend on the smooth structure in question? And that question turns out to be a really useful way for probing smooth structures on X. Now in a different direction, if I have some geometric structure on X, like a complex structure or a symplectic structure, can I ask the surface sigma to respect that structure in some way? So now is a particularly concrete question that we'll think about today. I want to ask, if I fix a knot in the three sphere, how many surfaces can it bound in the four ball? So that's just one particular question. But in general, I want to make the definition that if we have two surfaces, sigma and sigma prime, in some four manifold X, we'll say they're exotically knotted, or simply exotic, if they're topologically isotopic, but not smoothly isotopic. So that is, they're isotopic through homeomorphisms of X, but not through diffeomorphisms of X. And throughout, we'll denote those notions using the notation below. So there's a rich history for the study of exotic surfaces. But one of the most important constructions is the rim surgery construction due to Fentuschel and Stern. Now the rough idea here is to start with some existing surface sigma and choose some simple closed curve gamma inside of sigma. And what we'll do is take an annular neighborhood of that curve gamma and use some knot in the three sphere to knot up that annular neighborhood. And so we get this modified surface sigma k, which we've depicted cartoonishly on the slide. And the question is, how does the surface compare to sigma? Now, topologically, we can guarantee that sigma k is topologically isotopic to sigma whenever X is closed and simply connected, and the complement of sigma is simply connected as well. Okay? But that's only half the battle. We need to know if sigma is smoothly isotopic to sigma k or not. And under favorable circumstances, we can show that it's not. And these conditions are broad enough to produce lots of interesting examples. But in particular, we'll ask that the surface sigma be symplectic, we'll ask that its genus be at least one, and then we'll have some condition on the curve gamma that we're using. It's going to have to be homologically non-trivial in sigma, and sigma is going to have to satisfy a certain self-intersection condition. And now once you have that arrangement, all you need to do is make sure that your knot K is sufficiently complicated. In particular, you want to make sure that it has non-trivial Alexander polynomial. So I want to highlight one other construction which uses the blowdown operation. And it's of note because it lets us get exotic surfaces that are two spheres. So the starting point is to take two four manifolds X and X prime that are homeomorphic but not diffeomorphic, yet they become diffeomorphic after connect summing with a copy of CP2. And so now that new four manifold naturally contains two copies of CP1, and because X and X prime are homeomorphic, there's a homeomorphism of this new four manifold carrying one CP1 to the other. However, there can't be any diffeomorphism of this new four manifold, taking that one CP1 to the other, because otherwise you could blow those two CP1s down and get a diffeomorphism between X and X prime, which we know can't exist. Now there's more to the story in the smooth setting that I can possibly cover here, but I want to shift perspectives for a moment to the complex setting. So in this case, we have some extremely strong rigidity phenomena. In particular, if sigma and sigma prime are homologous closed complex curves in a closed Kähler surface that's simply connected, then sigma and sigma prime are automatically smoothly isotopic. So this doesn't leave any room for smoothly exotically knotted surfaces. And the point is that if two surfaces were topologically isotopic, then they'd necessarily be homologous. And so now they're smoothly isotopic as well. And so it's natural to ask, in the softer symplectic setting, does any of this rigidity persist? And so just to recall, what do I mean by that symplectic setting? Well, we have some four-manifold X with a symplectic two-form omega, which is a closed two-form such that its square is a volume form. And we'll say that a surface in X is symplectic if omega restricts to a symplectic, i.e. area form on sigma. And one of the most important conjectures in this area is the symplectic isotopy conjecture. And it posits that any two homologous symplectic surfaces in CP2 are in fact symplectically isotopic. And so this is verified up through at least degree 17. And there's one other rigidity result that I want to mention, which is a compilation of work of several people, but largely working off of results of McDuff. And it says that in a symplectic four-manifold with either empty boundary or convex boundary, any symplectic two-sphere with self-intersection at least -1 is unique up to isotopy in its homology class. So this gives us some context in which especially spheres in symplectic four-manifolds are particularly rigid. And for the results I mentioned, even just the homology class determines the smooth isotopy type. However, this principle fails in general. And so combining work of several authors, we get the following result, which is that for any genus greater than or equal to 1, there are symplectic four-manifolds containing symplectic surfaces sigma and sigma prime of genus G that are homologous but are not smooth isotopic. Indeed, there's no diffeomorphism of X taking one surface to the other at all. A couple remarks on this set of results. All the surfaces involved have self-intersection 0, and that arises because of the underlying construction, which begins with an initial symplectic surface and takes parallel copies of it and braids them together in some sense. Now, the surfaces constructed can often be distinguished using the fundamental group of their complements, but there are subtler examples that require more machinery like Seiberg-Witt invariance. Now, for genus 1 and presumably higher, you can get examples where the complements of the surfaces are simply connected, and then that will let you conclude that the surfaces are topologically isotopic and therefore smoothly exotic. Okay, so where does that leave us? The problem that I want to state today is that to date, all the constructions of exotic surfaces have at least 2 out of the following 3 limitations. What are those? Well, 1, the surfaces are required to have genus at least 1. 2, to conclude that there is some topological isotopy between the surfaces, generally require that the surface complements are either finite cyclic or simply connected. And finally, even if one surface is symplectic, in general you can't make the other surface symplectic. So existing constructions have at least 2 of these 3 limitations, if not more. And so my goal today is going to be to outline a new construction of exotic smooth and symplectic surfaces, including some ones that fill in those gaps. So here are the main results I want to tell you about today. And the first one gets towards that question that we asked at the beginning of how many different surfaces in the 4-ball a knot in the 3-sphere can bound. And so our statement is that for any genus greater than or equal to 0, there exists infinitely knots K in the 3-sphere, such that K bounds a pair of smooth surfaces of genus G in the 4-ball that are topologically isotopic, but are not equivalent under any ambient diffeomorphism. Now I want to plug some really nice work of Juhas, Miller, and Zemke, who recently constructed other exotic surfaces in the 4-ball using a fundamentally different approach, and I'll make some comments about those later. So getting back to this construction, the particular surfaces we construct can be realized as complex curves in the 4-ball inside of C2. And so, for example, if we take the case of genus 0, we obtain holomorphic disks in the 4-ball whose branch double covers turn out to be exotic contractible Stein domains with the same contact boundary. So these sort of independent interest. And now these complex curves are also symplectic surfaces. And so by capping off these surfaces inside of larger symplectic four manifolds, we obtain the second theorem, which says that for any genus greater than or equal to 0, there exist convex symplectic four manifolds X containing symplectic surfaces sigma and sigma prime of genus G that are topologically isotopic, but they're not equivalent under any ambient diffeomorphism. So in particular, these are the first examples of smoothly exotic symplectic two spheres in symplectic four manifolds. But this construction also has other ways in which it diverges from existing constructions. For example, we can have arbitrarily large and negative self-intersection for these surfaces. Okay, so to illustrate these theorems, we're going to take as a running example a particular knot in the three-sphere with a particular pair of disks that it bounds. And we'll use these to give examples of the first theorem and then sketch how they can be applied to obtain the second theorem. But here's our example. So I want you to consider the knot K that's shown here on the left. And the thing to note is that it bounds a natural ribbon disk that's ribbon immersed in S3 as drawn, but which naturally embeds in B4 by pushing it down at the points of self-intersection. Okay? And I want to recall that the four-dimensional notion of ribbon is that a surface in the four-ball is ribbon if it has no local maxima. And so in particular, this surface D, once embedded into the four-ball, will have no local maxima. Now there's a different way we could describe D, which is using a band move. It'll be the same surface, but drawn in a slightly, or presented in a slightly different way. And so here we have that description. So if we look at the copy of K in the top left, there's this blue band on the bottom right part of it. And if we surger the knot along that band, as perform a band move or a saddle move along it, we get this diagram on the top right, which turns out to be a two-component link. And if we work and simplify it, we see that that two-component link is just an unlink. And so then each of those unknotted components can be capped off with a minimum. And so we obtain a description of D using one saddle and two minima. Now with this perspective in mind, we can go hunting for other disks by looking for other band moves. And indeed, we can find such a band move that gives rise to a different disk, D prime. So now in this sequence of diagrams, if we look at the top left, there's a green band. And if we perform a band move along that band, then we get the two-component link in the top right in the figure. And one of the components to help distinguish them has been shaded in as green. And now working through the rest of the diagram, we see that this also simplifies to a two-component unlink. And therefore, by putting in two minima, we obtain a different disk, potentially D prime for K. Now, the key claim is that these are going to be smoothly exotic. But to start off, we need to show somehow that they're topologically isotopic. And so that's our first order of business. The key ingredient is going to be a recent theorem of Anthony Conway and Mark Powell that builds on earlier work of Friedman and Quinn. And it states that any pair of ribbon disks in the four-ball that have the same boundary and whose complements have infinite cyclic fundamental group are going to be topologically isotopic rel boundary. And so this criterion is useful because it's particularly easy to verify in practice. I do want to note that it's false for genus greater than or equal to 1. That follows, for example, from work of Takahiro Oba. And what this means is that when we want to try to look to constructing exotic surfaces of higher genus, we're not simply going to be able to try to make them have infinite cyclic fundamental group for their complements and be ribbon, but rather what we'll do is start with some ribbon disks that are exotic and then attach bands to increase the genus. Okay, so with this key ingredient in hand, how do we prove that the disks D and D prime are topologically isotopic? Well, we can use the descriptions of D and D prime using band moves to write down handle diagrams for their exteriors. And then we can read off the fundamental group presentation from those handle diagrams, check that it is indeed infinite cyclic, and then appeal to the theorem above. And that'll tell us that D and D prime are indeed topologically isotopic. Okay, so we said that we want to show that these disks D and D prime are smoothly exotic. But before distinguishing them smoothly, I want to note that we can generalize them. So K can be generalized to a family of knots Km by introducing M right-handed full twists along the 4 strands that pass through the box as shown in the diagram below. And the sort of point to note is that for all M, all integers M, the knot Km bounds a pair of disks D and D prime constructed just as before, and they'll be topologically isotopic. So the whole construction and argument runs through when we introduce these twists to get an infinite collection. So how do we actually go ahead and distinguish these disks? What we'll say is that for m equals 0, which is just the original knot K, and for m much large and sufficiently negative, we'll show that there's no diffeomorphism of the 4-ball carrying D prime onto D at all. And I want to point out that the statement is almost surely true for all m less than or equal to 0, but the argument that we'll give in particular only applies for m equals 0 and then large negative m. And so I'm going to outline what the strategy here is. And the first step is to find some knot J in the complement of your knot K that bounds a disk in the complement of D prime, but hopefully not in the complement of D. And so that should be hopefully picking up on the difference between D and D prime. So as an example, a natural candidate is to take a knot which just runs one time around the band that we used to define D prime. And the reason is that when we perform that band move, we sort of part the seas for J to go ahead and bound a disk. That is, as we descend down into the 4-ball, we see an opening appear between those 2 strands, and then now we can plug in a disk bounded by J. However, when we're thinking about the disk D, that band doesn't necessarily exist in the surface, and so we have no reason to believe that J should bound a disk in the complement of D. Now with this candidate in mind, what we want to do is start to study it, this candidate knot J. So the second step is to prove that any diffeomorphism of the 4-ball that might take D prime onto D has to fix J up to isotopy. And so this is really a statement about diffeomorphisms of the 3-sphere that fix the boundary of the disk, the knot K. And using some techniques from hyperbolic geometry and some direct calculations related to this particular knot K and Km, we can indeed prove that any diffeomorphism of S3 fixing K must fix J up to isotopy. And so now that we've got this candidate that we can sort of control, our third step is to show that J cannot bound a disk in the complement of D. So in our particular case, the strategy is to actually look at the lifts of J into the double-branched cover of S3 over the knot Km. Now, why do we want to study those lifts? Well, the point is that if J bounded a disk in the complement of D, then when we take the branch double cover of the 4-ball over our disk D, the disk bounded by the curve J would lift to disks bounded by the lifts J tilde. And so now our strategy is that we look at the branch double cover of B4 over D, look at the lifts J tilde of J, and use an adjunction inequality to show that those lifts cannot bound a disk in the branch double cover. And so that tells us that there couldn't have been a disk downstairs, and so the conclusion is that there cannot be any diffeomorphism of the 4-ball taking D prime to D, because it would take the disk bounded by J in the complement of D prime to a disk in the complement of D, but we just proved that no such disk can exist. Okay, great. And so summarizing the past few claims, we have that for m equals 0 and for large negative m, the disks D and D prime in the 4-ball are smoothly exotic, which was the sort of genus 0 case of what we wanted to show in the first theorem. Now, for higher genus, there are a couple options, but the simplest thing to do is to take, for example, the standard genus G slice surface for the T2 2G plus 1 torus knot and simply boundary sum it onto each of these disks D and D prime to get some genus G surfaces S and S prime. And for these particular choices, it's easy to check that the previous construction and argument goes through, and we can distinguish these surfaces using their branch double covers. Okay. So now, with the last few minutes, I want to shift back to the complex and symplectic settings. And we have the following claim, which the first part says that the surfaces S and S prime that I just described can be isotoped to be symplectic with respect to the standard symplectic form on the 4-ball. And with an eye towards the complex setting, we can show that there are pairs of complex curves in the four-ball C and C prime, such that the pairs of B4 and C and B4 and C prime are diffeomorphic to the pairs B4S and B4S prime, respectively. So we can actually realize those exotic smooth surfaces S and S prime as complex curves up to diffeomorphism in the four-ball. So part A, that's proven rather directly, and it uses this idea of ascending surfaces in C2. Part B, on the other hand, is a little less direct and appeals to some deeper work of Gromov, in particular using some arguments of Boileau-Revkov and Rudolph. Now, we also really want to get exotic surfaces that are symplectic and closed. So to do this, we can take the symplectic surfaces produced in the four-ball by the claim above, and since they have the same boundary, we can attach a two-handle to the knot K formed by their boundary, and for sufficiently negative framings, we can use the construction of Dave-Gay to realize these as symplectic two-handles. In this case, the core disks of these symplectic two-handles are also symplectic. So what we obtain is a convex symplectic four-manifold X obtained from the four-ball by attaching a single two-handle, and inside that four-manifold, we can cap off our surfaces S and S prime to yield closed symplectic surfaces sigma and sigma prime. And now, for these particular choices, it turns out we can run the previous argument using double branch covers and again distinguish the surfaces sigma and sigma prime. All right, so in closing, I just want to make a few remarks about these proofs and results. And the first is that I expect that these results can be extended to closed symplectic four manifolds, but the obstruction is going to need to change. And the point is that we were using the adjunction equality for surfaces in Stein domains, but that's not going to apply in the closed symplectic setting. The second point I want to make is that similar techniques to the ones described above can produce the first examples of Lagrangian two spheres in Stein domains that are homotopic but aren't topologically isotopic. And so this fills another gap in the literature. And now finally, there are some connections with Heegaard-Floer homology to sort out. And the question I have in particular is, can the exotic disks D and D prime in the four-ball be distinguished using the cobordism maps they induce on link-Floer homology? And this relates back to the work of Juhas, Miller, and Semke that I mentioned, because they used a variant of rim surgery to produce exotic copies of surfaces in the four-ball with positive genus. And they were able to distinguish those using the link-Floer TQFT. So it's natural to ask, given this different construction, and in particular given the case of genus 0 surfaces, can the link-Floer TQFT see the difference between these surfaces? All right, so I'll end it there, and thanks for listening.